Hello everyone, let's go ahead and start our chapter 18. So in this chapter we're going to learn reactions of benzene and substituted benzene. Okay, so all of you guys know how a benzene molecule look like. So this is benzene, this molecule. So this chapter begins a discussion of the families in group 4. So in the families in group 4 we have benzene rings, and also this is also aromatic ring, substituted benzene with a nitrogen. This is pyridine, and then you can also have pyrrole rings where this Z atom could be nitrogen, oxygen or sulfur. Okay. Benzene is an aromatic compound. You can also see that we can draw the resonance structures for benzene. Okay, so these two are resonance structures. And if you look at the electrostatic potential map for the benzene, you can see there are hydrogens on the outside. There are 6 hydrogens, and there are 3 pi bonds inside the benzene ring. So the inside the benzene ring, it is more electron denser. That's why you have a red color towards the middle of the benzene ring. It's a cyclic compound. It is planar, has an interrupted cloud of pi electrons, and has 3 pairs of electrons in the pi bond. It is an unusually stable compound. Benzene is aromatic. Normally, we know if you have a double bond in a molecule that they are very reactive. So the double bond, you add bromine, the bromine will add across the double bond. But for the benzene, since there are, even though it has 3 double bonds, they are conjugated and resonance stabilized, and because of that they are very stable. So they would not normally undergo reactions that would a normal alkene would undergo. Okay, so it is unusually stable compound. So these are some of the substituted benzene that we can find in nature. So here we have a benzene ring. We have this handle on the benzene ring. This is ephedrine, a bronchodilator. And this one is it's hard for me to read it. Antibiotic that is particularly effective against typhoid fever. You guys try pronouncing this, okay? Okay, and this one is mescaline, active agent of the peyote cactus. You can see that there is a benzene ring, and there is a 3-methoxy group, and then you also have a amine group. Okay, so but we are looking at the benzene ring. Here's adrenaline epinephrine, a hormone released by the body in response to stress. So when you are under stress, guess what? You are releasing benzene ring with bunch of other functional groups, and this is adrenaline. Okay. Some drugs have substituted benzene rings, and this drug, Lexapro, antidepressant. You can see there are 2 benzene rings, and this one has this benzene ring over here. A Plavix, inhibitor of platelet aggregation, and then this is Zyrtec. It has 2 benzene rings. This is an antihistamine. And some substituted benzene appear in commercial compounds. So this is appetite suppressant, this molecule. Again, we can see benzene ring in it. And this is methamphetamine, this molecule again with the benzene ring. Excuse me. Aspirin, we all know about it, acetyl salicylic acid. So this benzene ring with the ester group and carboxylic acid. And this is found in saccharin, which is artificial sweetener. And this one in mothballs and air fresheners, that the smell that you get when you put mothballs, sometimes we used to put this in our cloth cupboards. It gives us a nice fragrance. And plus the mothballs help to get rid of any insects kinds that would attract to clothes and all that. Okay, that also has a benzene ring. And these are some of the benzenes that are toxic: 2,4-D, 2,4,5-T, TCDD, Vietnam War defoliation mission. So for that, these toxic benzenes has been used. Okay, so let's see how we can name these monosubstituted benzenes. Some monosubstituted benzenes are named by adding the name of the substituent to benzene. Adding the name of the substituent to benzene. So now this is a bromine. It will be bromobenzene, chlorobenzene, nitrobenzene, and this is ethylbenzene. Some monosubstitute benzenes have names that incorporate the substituent. Now this one is methylbenzene, but it looks like nobody's calling it as methylbenzene. It always been called as toluene. And this is phenol. We don't call it as hydroxybenzene. It's phenol. Aniline, benzene sulfonic acid. This is anisole, benzene group with a methoxy group. Anisole, styrene. So this is used in polymers. This is styrene. So this is benzaldehyde. This is benzoic acid, and this is benzonitrile. We have come across these molecules before also, right? And then we also need to know what is the difference between the phenyl and benzyl substituent. Phenyl group is this group where you have only the benzene ring. We call it as a phenyl group. So this could be any other substituent. You can have a chlorine here. Okay, so this is a phenyl group. But the benzyl group is when you have a benzene ring attached to a CH2 group. Do you see the difference? Phenyl is when you have only the benzene ring. The benzyl group is benzene ring with a CH2 group. Okay, that's the benzyl group. Now see how this is being named. So this one is chloromethylbenzene, or we can call it as benzyl chloride. Benzyl chloride, because this is the benzyl group. Okay. If you have a chlorine here, you can say either chlorobenzene or phenyl chloride. Now this one, there are two phenyl groups, and this is an ether. We can name it as diphenyl ether. Okay. Whereas this one, there are two benzyl groups. You see here, benzene ring and CH2 is called benzyl. So there are two benzyl groups. So this is dibenzyl ether, and this is diphenyl ether. Alkyl substituted benzenes. Now in this one, the first one, you have an alkyl group, and this alkyl group has a common name, which is isopropyl. This is a propyl because it has 3 carbons. Iso means when the carbon has 2 methyl groups and a hydrogen. So this is isopropyl benzene. And this one, it has 1, 2, 3, 4 carbons. And then if the second carbon of the butyl group has a substituent, we call it as a secondary butyl group, because this carbon is secondary because it has a hydrogen and 2 alkyl groups. It's a secondary. So the common name for this one is secondary butyl. So we can say secondary butyl benzene. Now this one also has 1, 2, 3, 4 carbons, and this carbon is a tertiary carbon, and 4 carbons butyl tertiary carbon. We call it as tertiary butyl benzene. Name as an alkyl substituted benzene when the alkyl group has a name. That's what we did for these 3. Okay. Otherwise, name as a phenyl substituted alkane. Now this one, 1, 2, 3, 4, 5. We cannot say this is secondary pentyl because this carbon also secondary, this carbon also secondary, this carbon also secondary. So we do not have a common name for this carbon in a pentane ring, pentane alkyl group, not a ring. Okay, sorry about that. So because of that, we're going to consider a phenyl as a substituent. Phenyl is a substituent on the alkane, so this would be named as a 1, 2, second carbon has a phenyl group, 2 phenyl pentane. Okay, and this would be 3 phenyl pentane. Name as an alkyl substitute benzene when the alkyl group has a name like this, and otherwise name as a phenyl substituted alkene like this too. Toluene, which is methyl substituent on benzene, is an exception. We always call it as just the toluene, which is this one is toluene. Okay. Aryl. So you will also come across this name, aryl. It means benzene or substituted benzene, aryl group. Okay, that's another name for the benzene ring or substituted benzene. So this is an aryl compound, phenol. Okay, and this one is bromophenol. Each of these structures could be abbreviated as aryl OH. AR meaning either benzene ring or just the substituted benzene. Okay, now this one is phenol. So you can say AROH, aryl and OH, because the phenol is the prominent substituent between halogen and alcohol, or a halogen or an alkyl group and OH group. So this is the phenol. On the phenol you have this alkyl group. So any of these can be abbreviated as aryl OH, AROH. Okay. How benzene reacts? Normally, benzenes would undergo electrophilic aromatic substitution. Since benzene ring has 3 pi bonds, resonance stabilized, so benzene ring is normally electron rich. So it would act as a nucleophile and it would react with the electrophile. So we call it as an electrophilic aromatic substitution reaction. Okay, so the electrophile, in this case Y, will substitute one of these hydrogens. Now there are 6 hydrogens on benzene. Each of these are equally capable of substituting with Y. Okay, so H will be gone and Y will be replaced. So it's a substitution. Aromatic compounds such as benzene undergo electrophilic aromatic substitution reactions. And this is the mechanism. And you will see this mechanism over and over again, but it's good to get it over here and understand it. So what's going to happen? The very first step is, now the benzene ring is normally stable. So the stable molecule is going to react with the electrophile. So that is a slow step. Okay, because now the stability is going to a little bit affect by having electrophile attack. So this is a slow step. So once the bond breaks, which bond are we going to break here? There are 3 pi bonds. So here you have a 1 sigma bond and 1 pi bond. It's always the pi bond that gives electrons to form a bond with the electrophile. So the 2 electrons are going to form a bond. So then what happened to the other carbon? Now this carbon has only 3 bonds. Earlier it had 4 bonds, 1, 2, 3, and what you are not seeing is the hydrogen there. Now it has 1, 2, and the hydrogen that we had over here. So it is now with the carbon with the 3 bond, you know that is a carbocation. It's a positive charge. So the benzene ring will become positively charged. And this charge can be resonance stabilized like this. So this pi bond opens up and form the double bond here. Now this carbon will become positively charged. And then you can draw another resonance structure. These all are carbocation intermediates. So the pi bond makes a bond with this carbocation and this carbon, generating another positive charge right there. Okay, so once the electrophile attach on the benzene ring, it can have these 3 resonance structures, 3 carbocation intermediates. So finally what happened is, now since it broke its stabilization, now any base in the medium will take up the hydrogen that is attached right on the same carbon as the Y is attached. A base will remove this hydrogen and regain the aromatic stability. So since we are regaining the stability it lost due to this process, this happens very fast. It's a fast reaction. Okay, So base in the reaction mixture removes a proton and regain the aromatic stability or the aromaticity of the benzene ring. Okay, an electrophile substitute for H plus. So you will see most of the reactions are going to take place according to this mechanism. So like in the previous chapters, you don't need to think too much about different types of mechanisms in the benzene ring. So here's the reaction coordinate diagram, and you can see it's basically your reactants and your products both have about the same stability because both of these are aromatic compounds. Okay, so first step is always the breaking of the aromaticity. So it needs some energy, free energy increases because it's going to attack to the electrophile, and then you have the intermediate carbocation, okay, formation of the carbocation, and then the removal of the hydrogen, go through a second transition state, and then it again the energy will be lost and become more stable since it gains the aromatic nature of the benzene ring. Okay, bromination and chlorination of benzene. So when you are adding a bromine or chlorine, it requires a Lewis acid catalyst. Okay, and the Lewis acid catalyst we use is iron bromide, iron 3 bromide or iron 3 chloride, ferric bromide or ferric chloride. In the presence of bromine, we can add a bromine group on the benzene. Same thing. If you want to add a chlorine, you add chlorine Cl2 gas in the presence of ferric chloride, Lewis acid catalyst. Because benzene's aromaticity causes it to be less reactive than an alkene. Remember we talk about that alkene is more reactive. If you just add bromine to alkene, alkene will become saturated by adding the 2 bromine atoms on double bond. But the benzene ring 3, even though it has 3 double bonds, they have added stability due to the aromaticity, so they would not just add bromine or chlorine to these double bonds. So it needs a Lewis catalyst. Okay, and here's how the mechanism of the formation of the electrophile for bromination and chlorination of the benzene ring. The first step is the generation of the electrophile. Now here you have bromine-bromine. It's a covalent bond. So the 2 bromine ions are attached to each other by a covalent bond. Now you can see they also has lone pairs on each bromine. Okay, so the lone pair can act as a Lewis base, and iron bromide is a Lewis acid because iron has 3 bromine attached to iron. So meaning it has only 6 electrons on iron in the Lewis structure. So if you are electron deficient, that is a Lewis acid. Electron lone pairs having can be donated as a lone pair, which is a Lewis base. If you remember the Lewis acid Lewis base definition in Gen Chem 2, which is what I just told you. Lewis base would be something that can donate a pair of electrons or a lone pair. Lewis acid is something that it has a vacant orbital which can accept a lone pair from another atom. So this is the Lewis base. It gives its electrons to the iron bromide. Now it's going to form this bond between bromine and iron. Okay, now what that do is this covalent bond between the bromine it become weaker now. Okay, since it become weaker, it's easy for this atom to lose. Okay, so it makes it a better electrophile. So donating a lone pair to a Lewis acid weakens the bromine or chlorine bond. So the next step, once the Lewis acid catalyst makes a complex with the bromine, now benzene ring can attack the bromine. So this attacks the bromine, so the bromine bond breaks, gives its electrons to the bromine positive charge over here, and you're going to generate this iron bromide, FeBr4. Okay, so now iron has 4 bonds. Now the formal charge would be Fe minus 1. So once this happens, so this carbon will become positively charged, since the pi bond gave its electrons to form the bond between carbon and bromine. So this carbon does not have electrons. It only has 6 electrons, so it is now positively charged. So the base will come and grab this hydrogen, and then they regenerate the aromaticity of the molecule. So just the bromine group is attached to the benzene ring, and then you have this BH plus. This is the base conjugate acid, and then you can also going to make HBr, HB plus, HBr, and then you're going to be forming FeBr3. Okay, so this hydrogen that lost going to react with one of the bromine in FeBr4, making HBr, and then the Lewis acid catalyst FeBr3 regenerated. Okay, these are the steps that we just talked about. Electrophile adds to the benzene ring. That's this step. A base in the reaction mixture removes the proton. That's this step. Removes the proton from the carbon that bonded to the electrophile. Okay, and the same way the chlorination takes place. You're going to first form this complex with the iron chloride. Okay, Lewis acid, and then the benzene ring attacks the chlorine, forms the carbocation intermediate, and then the base takes up the proton, and then you can get the product where you have a chlorine added to the benzene ring. Okay, same process. Catalyst for bromination and chlorination. Because ferric halides mean these guys, ferric halides react readily with moisture in the air, they are generated in the reaction mixture from iron fillings and bromine or chlorine. So this is how the catalyst is being formed. So you add iron fillings and then the bromine, or iron fillings and the chlorine, and make the iron bromide or iron chloride in the reaction mixture. For the iodination, if you want to add iodine, we need to use a different route. Whereas here you use benzene ring, react with iodine in the presence of hydrogen peroxide and sulfuric acid. And this is how the electrophile is generated. Hydrogen peroxide with sulfuric acid and iodine, it's going to generate 2I plus, a water molecule, and hydrogen sulfate, conjugate base of the sulfuric acid. Once the electrophile I plus is generated, so this is going to add on to the benzene ring. Pi bond attacks the electrophile, same thing, the positive charge is formed. Carbocation, base removes the hydrogen and then regenerate the aromaticity of the molecule. Electrophile adds to the benzene ring, base in the reaction mixture removes the proton from the carbon that form the bond with the electrophile. Okay, so that is how we normally add halogens to the benzene ring. Now this is nitration of benzene. We have done this reaction, in fact, in the lab, which is, I believe, is our first experiment, nitration of phenacetin. That's what we did, right? Nitration, and we also learned about the mechanism. So this is how the nitration is done. So you have a benzene ring. You add nitric acid and sulfuric acid together. So these two together forms the nitronium ion. And then that will be added to the benzene ring. Okay. And we'll see how the nitronium ion is being formed. So this is the nitric acid. And if you draw the Lewis acid of the nitric acid, this is the Lewis acid. Nitrogen has a double bonded oxygen, singly bonded oxygen, and an OH group. Now nitrogen in this Lewis structure has 1, 2, 3, 4 bonds, which makes nitrogen +1 formal charge. Oxygen having 1 bond and 6 lone electrons make oxygen -1 formal charge. And if you remember, when you draw the sulfuric acid Lewis structure does not have any positives or negative charges. Okay, so the nitric acid, so between these two, since okay, wait, so the OH group over here, okay, nitric acid, this oxygen having 2 lone pairs, going to go and grab a hydrogen from sulfuric acid, okay, and forms a protonated OH group, meaning now you have a good leaving group, which is a water molecule. Okay, oxygen with 2 hydrogen carrying a positive charge. Now it's easy to lose a water molecule than a hydroxy group to generate the nitronium ion. So that is the reason this first get protonated. Okay, by any of these getting protonated, that will not happen. Okay, so now once you have a positively charged oxygen with 2 hydrogens, this can just fall off because you are losing a neutral water molecule, generating a nitronium ion, NO2+. That is the electrophile that we need for the nitration. These are the steps. Sulfuric acid protonates nitric acid. Protonated nitric acid loses water to form the electrophile, which is the nitronium ion. And this is the electron density molecule of the nitronium ion. Okay. And then the mechanism. So again, the same mechanism. One of the pi bonds attack the nitronium ion, and then this pi bond breaks. NO2 group will be added onto the benzene ring on this carbon. You still have the hydrogen that you had to begin with, and then now here you are losing 2 electrons, making a positive charge. So the base grabs the hydrogen, and then the nitration is done. Electrophile adds to the benzene ring. Base in the reaction mixture removes the proton, and then the carbon form the bond with the electrophile. Base in the reaction mixture removes the proton from the carbon that formed the bond with the electrophile. So that is the nitration, and now it is a sulfonation of benzene, adding a sulfonyl group. Okay, how do you do that? So the sulfonation, you heat the benzene ring. So this symbol represents heating with sulfuric acid. So you can add sulfonyl group on the benzene ring. And this is how we can generate the electrophile for the sulfonation. So it's 2 sulfuric acid. So this is 1 sulfuric acid, this is 1 sulfuric acid. Again, one of the OH groups of the sulfuric acid. Now remember, this is not a base. Okay, normally sodium hydroxide is a base when you have OH, but sulfuric acid, this hydrogen is acidic, but this oxygen has a lone pair that grabs a hydrogen from another sulfuric acid molecule, generate a protonated water molecule here. So then this molecule can fall off, generating the sulfonium ion and water. Okay. And then the sulfuric acid protonates sulfuric acid. Protonated sulfuric acid loses water to form the electrophile, which is a sulfonium ion. Mechanism, same mechanism. Pi bond attacks sulfonium ion. Base comes and removes the hydrogen, and then we have a sulfonated benzene ring. These sulfonic acids, they are strong acids. Okay, so this is benzene sulfonic acid. pKa is -6.5, meaning very acidic. Because now, how do we look at a stability of an acid, and or to find out whether an acid is stronger? We always have to look after the acidic proton. is removed, how stable is the resulting structure. So in this molecule, this is the most acidic hydrogen. Once this is been removed, we're going to be making this benzene sulfonate ion. And you will see this benzene sulfonate ion is very stable because we can draw many resonance structures, meaning delocalizing the electrons on this oxygen atom. Always a localized charge is unstable if it is more delocalized, meaning electron density is not in one particular atom. Okay, that will make the molecule or the ion stable. Sulfonic acid is a strong acid because its conjugate base is particularly stable. So this is the conjugate base. Negative charge in the benzene sulfonate ion is delocalized over 3 oxygens. All of these 3 oxygens, it's delocalized. Okay, you can in fact draw the resonance structures and see the delocalization. So the low electrons on this oxygen, if you draw the Lewis or the dots, you can see there are 6 electrons. So one of the lone pairs gives its electrons to form a pi bond between this oxygen and sulfur. Then one of these bonds can break, and you can draw another resonance structure have a negative charge on this oxygen. Similarly, you can draw another resonance structure having negative charge on this oxygen. So likewise, you have 3 resonance structures for the benzene sulfonate ion that gives that added stability and make benzene sulfonic acid is very acidic. Okay. And this reaction is reversible. So benzene sulfonic acid, if you heat it at 100 degrees Celsius with the acid, we can just get rid of the sulfonyl group and get the benzene. And similarly, if you heat up, if you do the reverse reaction, these two, the reverse reaction will give you benzene sulfonic acid. If benzene sulfonic acid is heated in diluted acid, hydrogen proton adds to the ring and the sulfonic acid group comes off the ring, which is the reverse reaction. This is the mechanism for the desulfonation, how we can remove the sulfonyl group. How do we do that? So again, the pi bond that is next to the sulfonyl group can react with a proton in the acid medium. So this is H3O+. Okay, so the hydrogen will add on to this carbon. Okay, so there are 1, 2, 3, 4 bonds. So the pi bond breaks and make a bond with this carbon with this hydrogen. And then you have this carbon will be positively charged. So then the sulfonyl group can give its electrons to form the pi bond again between these 2 carbon atoms. Why does it do that? Because right now it's unstable. But regaining the aromaticity makes it much more stable. So now it can fall off. Electrophile adds to the benzene ring. Sulfonyl group is eliminated from the ring. Okay, I guess we'll stop.